Now in this last part of the question, we're told that a buoy of mass 30 kilograms stands on the beam at a point D and the beam remains in equilibrium. We're also told that the magnitudes of these two reactions are equal. And if they're equal, let's just get rid of these subscripts here. Okay, so let's get rid of that one and that one. So we both got them set now at R newtons. And what we've got to do is find out the distance AD. So if this buoy of mass 30 kilograms stands at a point D on this beam, where are we going to place D? Well, technically it doesn't really matter because the maths will work itself through, okay, and tell us where D would be. But it does help to think ahead of the problem. Where do you think it's going to be? Do you think it's going to be on the left of the 20G or to the right? Well, it's going to be just to the right. Why? Because you can see that if we just look at this part of the beam, the weight here is closer to this reaction. So at the moment, this reaction would be a lot more than this one. But if they're to be equal, then I've got to push more of the weight towards this one, so the D has got to be over here. So I'm just going to put D down here, but it really doesn't matter. It would be a good experiment for you to do if you just try placing D, say, on this side. Now, we know that the buoy has a mass of 30 kilograms, so this is going to be 30 G newtons. And I'm going to work with the distance CD. I'm going to call that distance X. Now you could place X anywhere you like. And again, you just need to experiment. It's the best way you can learn with problems like this. Do it one way, but try and do it other ways so you can compare the methods. So I'm going to put X here. Now if you'd put D over here, I would have still labelled that distance X. Do the mathematics, X will turn out to be a value more than 2 when you're done. Okay, so it doesn't really matter. Okay, so how are we going to find out AD? Well, we've got to find out X first of all. And to find out X, what I'd want to do is first of all resolve upwards to get what R is, because I can see that if we took a moments equation, which is going to involve X, I'm also going to have an R involved in my moments equation. So I'll have two unknowns, X and R. So seeing ahead of that, I'm going to resolve vertically, and that will allow me to have an equation with one unknown. It'll be R, and I'll be able to solve it. So if we resolve upwards, we've got R plus R, or 2R obviously, and then we've got these forces downwards, minus 20G and minus 30G. And we know that these forces keep the rod in equilibrium. There's no resultant force, so that resultant force here equals 0. So if we simplify this, we've got 2R, and we've got minus 20G minus 30G, which is minus 50G, and if we add it to both sides, we end up with 2R equals 50G. And dividing both sides by 2 gives us that the normal reaction R is going to be 25G. 25G newtons then. Now that we've got R, we can take moments about any point. And the best place to take moments about would be C, because this would just give us an equation with easy values of X. You could take about B, it's up to you. You could even experiment taking moments about B, and it's good exercise. See if you get the same answer. So let's take moments about C, and we need to set up a positive sense. Technically it doesn't matter which way you go, anti-clockwise or clockwise, but I can see that if we take moments with the positive sense clockwise, we're going to involve a positive X, and that just makes the equation simpler. So I'm going to go in a clockwise sense. So if we start then with, say, the 30G newtons, we've got, for the moment, remember moment is force times the perpendicular distance to the point that you're taking moments about, we would have 30g times this distance here, which is x. So we've got 30g multiplied by x, 30gx then. When it comes on to the 20g, that too is going to turn it around c in a clockwise direction, so that will be positive. So it will be plus 20g, the force, times the distance to c, which is 2 meters. So 20g times 2. And then we've got this force acting at B, this reaction here. We've already found out that that reaction is 25g now, so we've got the 25g, but it's going to want to turn the rod in an anti-clockwise sense about C. So that's going to be negative. So minus the r, 25g in other words, multiplied by the distance to C, which you can see is 3 plus the 2, a total of 5. This force here has no effect through C, no turning effect at all. So we've done all the forces now, we've done all the moments, so what is the resultant moment? Well, because it's in equilibrium, it's going to equal 0. So it just means that we can find out what x is now in this equation. So what we've got then is 30gx, let's just put therefore 30gx, this is plus 40g, and then we've got minus 125g, and that equals 0. So if we group these two together, we end up with minus 85g. So we can add 85g now to both sides, and you end up with 30gx equals 85g. Divide through by 30g, and you've got 85g over 30g, and you can see that the g's cancel, no need to work those out. 85 divided by 30 gives you x equaling, let's just put therefore x equals 2.83 recurring, or you could just write 333 and so on. So therefore, to get the distance a to d, which is what was asked in the question, I've just got to add this extra 1 meter. So a to d is going to equal 1 plus that, so that's going to be 3.8333 and so on. And if we round that, say, to 1 decimal place, a to d is going to equal 3.8 meters to 1 decimal place, 1 dp. Okay.